then you would use A and B. Okay, so now I'm going to put them into my formula here. On top will be 0.916.
Ms. Nussbaum, wouldn't it be 0.912?
Yes. Oh my gosh, go get a prize.
Thanks, Gustavo.
Embarrassing when I'm doing like correlation coefficient hypothesis testing with 2 samples and then I can't round. I had a professor like that. He was a genius, and I'm not saying that I'm a genius, but this guy was. This guy was like a straight Einstein, and he looked like one too. He had like crazy white hair that stuck out everywhere, and he wore the same sweater to class every single day. He taught at UW-Madison. I was pretty sure that it was like one of those like work sweaters that he just got cold every day and threw it on over top, but like every day it was the same sweater. And he had a bit of a belly, so when he walked across a chalkboard, his belly would sometimes like erase like the bottom part as he walked. And he'd always be like so excited about stuff. And then one day he came in with a different sweater on and everybody like applauded and he had like no idea. And he's like, well, thank you. You know, like he's like so happy and stuff. But he would all the time, he'd be doing like brilliant math. He'd be like, he was really bored teaching calculus. He hated it. He'd be like, oh, we gotta learn derivatives again, you know, like basic derivatives. And everybody's like, what's a derivative in this room, right? And I know what derivatives are, but I don't think that they're basic. But he thought they were so boring and basic. And then he'd be like, do you guys want to know how a telescope works? And we'd be like, okay. And he'd be like, well, this is how it works. And he'd like explain it for like an hour. And then you would go to your TA session where there was like smaller groups. Because at UW-Madison, we had like, you'd have like calculus every day. And then 3 days a week, you'd have the main professor. And he'd be like in a lecture hall of 300 people where you'd just be taking notes and listening. And then 2 days a week on Tuesdays and Thursdays, how it worked out for me, we'd have a TA, which is like a graduate student who would have a class of 20. And then he'd like answer all your questions or whatever, and you talk to somebody and actually get your questions answered instead of in a 300-person lecture where you couldn't. And the TA every day had to be like, well, we were supposed to learn about the derivatives of this, so I guess I'll teach you that today. You know, like, and it was always just our professor was like, I got excited about telescopes, you know, and then we'd be like, writing, and then we'd like talk to the TA, we'd be like, is telescopes on the test? And he'd be like, no, they're not. We're supposed to be learning about this, so let's talk about the quotient rule. And I'd be like, okay, throw away the telescope stuff. 1 minus, I guess this is slightly helpful, the R squared is already in there. What?
You weren't allowed to ask questions in like the big group?
In 300 people?
Yeah.
No.
Oh.
I mean, I guess you could, but nobody did. It was pretty standard that like your TA class is the one time when you ask all your questions and that the lecture was just a professor. And then he had office hours where you could go ask him questions. And 8.
It will be.
So I got 0.912 divided by the second square root of parentheses 1 minus 0.831 parentheses divided by 8. I got about 6.27. You guys get the same thing? That sounds like a no.
2, 8, that's that 9.
Well, I did 0.9.
6, 7.
6.2 is right.
1.62747.
Yeah, you probably did something slightly different than I am, because I didn't use this and squared it. I used the R squared from my calculator, so I just got a slightly different number. But either way, it's hitting way over here, which means, did you put parentheses here?
Oh, didn't do square root.
That'll do it, yeah. Okay, all right, so what do we say?
We do not, reject the null, accept the claim.
Reject null, but what does accepting the claim mean? What is the claim?
That
That there is a correlation.
Yes.
Oh, yes.
So really, there is not necessarily any claim in this one. You just know that significant correlation coefficient happens over here in the tails. So you would say, I reject the null, and then you would say the correlation coefficient is significant.
Can you explain that? I don't really understand.
So the reason why a correlation coefficient being significant would be in these tails is because 0 is right here. And if you remember, like if something has a perfect positive linear correlation, it's 1. And if it's a perfect negative correlation, it's -1. So the further it goes out on this test on either end, like if it had a really strong negative correlation, it'd be over here in the tails. If it had a really strong positive correlation, it would be over here in the tails. And this is the line in which we're accepting it. These right here are not R. They're just our lines from the t-test that we want to go past. Yeah, so this one is definitely a significant positive. Can you guys understand why it's a positive? Because it's way over here on the right. So it's a significant positive linear correlation between these two, which means that the more money a country spends, the more money their CO2 emissions are.
So significant means.
Significant is a line based on this 0.05. So if I had said I want to be 95% confident, this is the line for being 95% confident. If I wanted to be 99% confident, this line would move over more. And it would take more it would have to be more significant for you to be confident, yep.
Don't we know it's already significantly positive because the R equals 0.91?
Well, it depends on what your line is. If I said I wanted to be 0.99999% confident, or if I wanted to be 99.999 confident, then this probably wouldn't be good enough. It'd have to be higher. So, like, remember yesterday we were talking about, like, what is the line in the sand? What is considered really, like, a strong positive correlation and what's not? And it really depends on what your alpha is, the error you're willing to make. The smaller your alpha gets, the more you have to prove. So 95 is pretty standard, though. All right, let's flipping it over to the back side. All right, you're going to try again. This time, what? With a partner. You're going to go to page 469 in your book. Okay. Now, I'll let you say that you don't want to do this if you don't want to do this. If you do want to do this, I say we do it with just one person's calculator. It's a lot of data. But this is very interesting.
Should we at least do it 2 so we don't put it in wrong?
Do you want to do it with 2? Take a look at the data.
Yeah, I haven't seen it right now.
Okay, so the question is this. Do you want to do this? I'm okay if you don't want to, if you want to go straight to the homework. The question is, which I think is